A function f has derivatives of all orders for all real numbers x. A portion of the graph of f is shown above, along with the line tangent to the graph of f at x equals 0. Selected derivatives of f at x equals 0 are given in the table above. Part A. Write the third degree Taylor polynomial for f about x equals 0. So, as we establish our third degree Taylor series by taking the summation from 0 to 3 of the nth derivatives, specifically at our centers, which in this case is 0, divide that by n factorial, and then multiply by x minus 0, again that being our center, raised to the n. We'll just quickly erase x minus 0 and rewrite it as x to the n. So we're going to need to figure out what f of 0 is, divide that by 0 factorial, and multiply that by x to the 0. But x to the 0 is, well, 1. 0 factorial is 1. So what we need to do is figure out what f of 0 is. And it doesn't tell us up here in the original part of the problem, but it does say that there is a graph of f, which is right here. And its height, specifically at 0, is 3. So we can say that f of 0 is 3, and we'll put that into that spot right there, and we'll move on. Next up, we have to add the first derivative at 0, divide that by 1 factorial, and raise that to the x to the first. Don't need the 1 here. 1 factorial is simply just, well, 1. So if we can figure out f prime, we'll be good to go. But again, it doesn't actually give us the information in the paragraph, but it does say that the line tangent to our point, specifically at 0, 3, is given to us. And that is given to us right here in the graph, and that line happens to be crossing through this point, and this point. So if we figure out that we're going down 2 units for every 1 to the right, we can establish that f prime of 0 is going to be equal to -2, which then will get multiplied by x. So we move on to the next term, in which the second derivative at our center 0 is now divided by 2 factorial x squared. We're not going to get this information from the graph, but this time from the table. Since it says that when n is 2, our second derivative is 3, it's pretty straightforward. We take plus 3 divided by 2 factorial and multiply it by x squared. We will complete this process again when we take the third derivative at 0, divided it by 3 factorial, and multiply it by x cubed. So we go back to the table. There's our 3. We find out that the third derivative at 0 is -23 halves. We go minus 23 halves, divide that by 3 factorial, we get x cubed, and we've got our third degree Taylor polynomial. Although the answer you have is completely acceptable for AP, if you have the time and you wish to rewrite it, and you can rewrite it successfully, then go 3 minus 2x. Remember that 2 factorial is 2, so that would be plus 3 halves x squared. And if 3 factorial is 6, we'll take -23 halves, multiply it by the same as 1/6, and that will become -23/12 x cubed. If you're trying to figure out why we didn't include this part of the table, it's because, again, it specifically said it's a third degree Taylor polynomial, so we stop with the third degree. Part B, write the first 3 non-zero terms of the Maclaurin series for e to the x. Write the second degree Taylor polynomial for e to the x, f of x, about x equals 0. So, e to the x's Maclaurin series is the sum of x to the n over n factorial as n goes from 0 to infinity. But in this case, we only want to approximate e to the x for the first 3 non-zero terms, which will then be 1 plus x squared over 2 factorial, and 2 factorial is just 2, so we'll just write it like that. So anywhere we need to approximate e to the x, we'll have to use this instead, which definitely makes more sense when we get to the second part of the question. Write the second degree Taylor polynomial for e to the x, f of x, about x equals 0. So before we go any further, remember that the second degree Taylor polynomial for f of x is going to come back from our answer in A. but that was a third degree polynomial. So we'll only focus on these terms right here, 3 minus 2x plus 3 halves x squared. So your first gut instinct is to write e to the x being multiplied by 3 minus 2x plus 3 halves x squared, and then distribute, coming up with 3 to the x minus 2x e to the x plus 3 halves x squared e to the x, and calling it done. This would be incorrect because e to the x is exact, and we're not using exact, we're using an approximation of e to the x, which we said was going to be 1 plus x squared over 2. So the real work is as follows. To approximate e to the x, f of x, we're going to say that that is 3 times 1 plus x squared over 2 plus, correct that, minus 2x of 1 plus x squared over 2 plus 3 halves of x squared times 1 plus x squared over 2. Now that seems like a lot of work, and it is if you don't take into consideration something very important. Once again, it says second degree Taylor polynomial is what we're going to predict with. And if we were going to actually multiply negative 2x to the x squared over 2, what we end up having is negative 2x cubed over 2. But that can't be used if it's a second degree polynomial because that term would have a degree of 3. So the easiest solution is just not worry about that particular piece in that quantity. We run into the same issue not once, but twice. If we multiply 3 halves x squared to x, that will end up producing an x cubed, or a third degree term, and 3 halves x squared times x squared over 2 produces x to the fourth, or a fourth degree term, and so these would both be issues, so we will not include those. So if you want to come up with your formula for e to the x times f of x, you will need to distribute the 3 to the quantity, coming up with 3 plus 3x plus 3 halves x squared. We will need to distribute negative 2x to 1 plus x and have negative 2x minus 2x squared. And then finally we'll have simply plus 3 halves x squared, which is multiplied by 1, which is just the same. And I think the best thing we can do is put our constants together, which really is just 3. We'll put our linear terms together, which is 3x minus 2x. And we'll put our quadratic terms together, which is 3 halves x squared minus 2x squared plus 3 halves x squared. And to come up with our second degree Taylor polynomial for e to the x, f of x about x equals 0, we will combine the terms saying 3 plus x squared. Part C. Let h be the function defined by h of x equaling the integral from 0 to x of f of t dt. Use the Taylor polynomial found in Part A to find an approximation for h of 1. So, if h of x does equal the integral from 0 to x of f of t dt, and we're going to use this up here, then we should probably write 0 to x. We'll need to use a placeholder variable, so we'll rewrite this as 3 minus 2t plus 3 halves t squared minus 23rd 12ths t to the third dt. But remember, the purpose of this question is to approximate h of 1. So, how about we erase all the x's and plug in 1 into their spots. So as we find the antiderivative, let's write 3t minus 2 halves t squared plus 3 over 6 t cubed minus 23/48 t to the fourth, going from 0 to 1. 0, 1 is going to make this much easier because literally our first piece is going to be 3 times 1, which is 3. Minus, well, 2 halves is just minus 1, so we could just put minus 1 there. 3/6 could have been written as 1/2, so I guess we could put a half here. And then minus 23/48 times 1 is minus 23/48. And as we subtract 0 into all the pieces, well, do we even need to write that? So let's just erase that. We don't even need the brackets here, and just figure out that all of that, 3 minus 1 plus 1/2 minus 23/48 works out to be exactly 97/48. Again, from an AP perspective, you could have stopped here, but it sure is prettier if you write it as 97/48. Part D. It is known that the Maclaurin series for h converges to h of x for all real numbers x. It is also known that the individual terms of the series for h of 1 alternate in sign and decrease in absolute value to 0. Use the alternating series error bound to show that the approximation found in Part C differs from h of 1 by at most 0.45. Now it tells us immediately that we're going to use the alternating series error bound. But I just want to kind of go back, look at the paragraph to understand why we can do that. First, it says that h will converge to h of x for all real numbers x. And since we are using h of 1, 1 is a real number of x, so we're good there. It also says that h of 1 alternates in sign, hence why it's an alternating series, but you can only use the alternating series test if it decreases in absolute value down to 0. So it meets all the conditions of the alternating series test, which shows it converges. This allows us to then use the alternating series error bound. Just to be clear, you don't have to actually say any of this because it's already given to you in the paragraph. I just wanted to make sure it was clear to you why you could use the alternating series error bound to begin with. But let's now actually work on the problem that's in front of us. If you're going to find the alternating series error bound, you have to understand that essentially the next term of our Taylor series polynomial would have given us the maximum error possible. Sometimes they'll refer to it as the first omitted term. So, back in A, then you would realize that we would need the fourth degree term. How would we have gotten the fourth degree term? Well, we would have taken the fourth derivative, specifically at 0, divide that by 4 factorial, and multiply it by x to the fourth. Well, lucky for us, we still have this particular piece of information in the table, where we can say that the fourth derivative happens to be 54. It would have been divided by 4 factorial and multiplied by x to the fourth. And that piece would have gone here if we would have continued on. This is what we're going to need to use to help establish what our error bound is. The problem is that is for f of x. We're being asked to find h of x, which means I should be adding plus 54 over 4 factorial t to the fourth into my integral. And when I take the antiderivative of that, I will have had 54 over 4 factorial times 5, t to the fifth, going from 0 to 1. So that's in fact exactly what I wanted to do. I wanted to take 54 over 4 factorial t to the fourth dt, realize that is the same as 54 over, and if you think of 4 factorial as 1 times 2 times 3 times 4 being multiplied by 5, you could actually just say it's 5 factorial t to the fifth going from 0 to 1. And then we'll basically realize that 54 over 120 is being multiplied by both 1 and then being subtracted by 0, which means you'll have 54 over 120, which works out to be 27 over 60, which works out to be 9 over 20, which happens to be the same decimal as 0.45 as expected here. And I can essentially say now that my error is going to be less than that next omitted term, which in this case is the absolute value of 9/20, which is therefore 0.45. And there's the work.